Today we are breaking down a brand new paper, Intrinsic Credit Assignment for Long Horizon Interaction by Auzina et al. From the Tübingen AI Center.
Just out, February 2026. And this one is a big deal for anyone in the RL and agent space.
The headline here is a new method called Delta Belief RL.
Right. And what they did with it is, frankly, astonishing. They trained a small language model, Qwen3, at just 1.7 billion parameters
Tiny.
to demolish a massive model like DeepSeek v3.2, which is, 670 billion parameters on information-seeking tasks.
And the mechanism is the real breakthrough. Instead of some huge external reward model, they use the model's own internal probability changes as the reward.
Exactly. It's so clever.
It's the aha moment of the paper for me. So if a question the model asks makes it more certain about the correct answer, it gets a reward.
Instantly.
Turn-by-turn feedback generated for free. And the result is an agent they call CIA, the Curious Information-Seeking Agent. It generalizes to completely new tasks, things like solving murder mysteries, way better than standard RL.
So, welcome to AI Paper Podcasts. Let's get into the technical details. We should probably start with the problem itself. Because, asking questions doesn't sound that hard for an LLM. Why are they so bad at something like 20 questions?
It's the classic difference between a fully specified problem and an underspecified one.
Okay.
LLMs are amazing at mapping an input to an output when you give them all the context. But with information seeking, the model starts out in a total state of confusion. It has no idea what it needs to know.
Right. It has to actively reduce its own uncertainty.
And web text, the stuff they're trained on, almost never shows the reason for a question. You see a question, you see an answer, but you don't see the internal monologue, the uncertainty that prompted it.
But the real technical hurdle is something else, right?
Yeah, it's the credit assignment problem.
Yeah.
This is a complete nightmare for long interactions.
This is classic RL. You play a 20-turn game, you win at the end. How on earth do you know which of your 20 moves was the good one?
Exactly. Let's say turn 5, you ask this brilliant question that just cuts the search space in half. But the other 19 questions are mediocre.
Mm-hmm.
If you're just using a sparse reward, a simple +1 at the very end, that signal gets washed out. The model has no way to credit that one heroic move at turn 5.
So the signal-to-noise ratio is just terrible.
Awful. And the only way to make it work is with massive, massive scale. The alternative is to train a separate critic model to give feedback at every step.
Which is super expensive. You're basically doubling your compute. And a good critic is often harder to train than the agent itself.
So you're stuck. Either inefficient sparse rewards or very expensive dense ones. And that's where Delta Belief RL comes in.
Okay, let's get into the solution. How are they pulling a reward signal directly from the agent's worldview?
It's all based on information gain. So in their training setup, like the 20 questions game, they know the secret word. Let's say it's bicycle.
Okay, so the training environment knows the answer, but the agent doesn't.
Right. So before the agent asks a question, the system pings it with what they call an elicitation prompt.
Basically asking the model, hey, what's the probability you assign to the word bicycle right now?
Precisely. And let's say at turn T, that probability is, tiny, 0.01%. Then the agent asks, does it have wheels? The answer is yes.
And now everything changes.
At turn tap +1, the system checks again. And now the probability for bicycle might have jumped to, say, 5%.
And that jump, that's the reward.
That's the reward. Delta belief is just the log probability at tet +1 minus the log prob at t. It's a direct measure of how much uncertainty was just resolved.
This is just so elegant. It's supervision, but it's basically free.
Yeah.
No human labelers, no separate critic model.
And it perfectly solves credit assignment. If a question gets a no answer that wipes out 90% of the other possibilities, the probability of the correct answer has to go up. The model gets an immediate positive signal for that exact turn.
Okay, but let me play devil's advocate. Just because the model's belief goes up, does that really mean it's on the right track? Couldn't it just be getting overconfident about the wrong thing?
That is a really short caution. And they actually validated this before they even started training. They ran a best event experiment.
Okay, what's that?
They'd take the base model, have it generate, say, 8 different candidate questions. Then they would cheat. They'd look ahead and see which of those 8 questions would cause the biggest positive update in belief.
And then just pick that one.
And performance went through the roof compared to just sampling normally. That proved the signal was a valid proxy for success.
So the signal is solid. Okay, let's get into the nitty-gritty. For all the ML engineers listening, what was the actual implementation stack?
The main task was the 20 questions game, or 20 Qs. The agent, the one asking the questions, was Qwen 3. They tried both the 1.7b and the 4b parameter versions.
And who was answering the questions? The Oracle.
That was a bigger model, Qwen 3 14b, acting as the user simulator. And they had a training set of about 1,000 secret words.
What about the algorithm? They used turnwise GRPO. Now, GRPO is Group Relative Policy Optimization. It's been getting a lot of traction, but it's usually applied to a whole trajectory.
That's the key difference. Standard GRPO looks at a whole game, gives it a score, and updates the policy. But because they have this delta belief signal at every single turn, they can calculate advantages per turn.
So they're not optimizing for the final win, they're optimizing for the immediate usefulness of every single question.
Exactly. And the reward function itself, which is equation 3 in the paper, has this one little detail that's actually kind of genius.
Go on.
The function is basically the final outcome reward plus lambda times the delta belief plus a penalty. But, and here's the trick, they wrap the delta belief term in a rate-LU.
A rectified linear unit. So they're clamping any negative values to 0.
Yes. This is so important. They only reward positive belief updates if the model asks a bad question, gets more confused, and its belief in the correct answer actually drops. They don't punish it. They just give it a 0 for that turn.
Why not punish it? Wouldn't that teach it what not to do?
Because exploration can be messy. Sometimes you have to follow a bad lead to rule it out. If you punish the model every time its belief drops, it becomes afraid to take risks. It just stops exploring. They found this positive-only shaping was the best way to encourage genuine inquiry.
And what about that lambda hyperparameter, the scaling factor?
They found the sweet spot was 0.1. If they set it too high, like 0.5, the training actually collapsed. The model just became obsessed with gaming its own belief score instead of actually winning.
And there was a small penalty for taking too long, right?
Yeah, a tiny negative reward for every turn, just to encourage it to be efficient. But what's interesting is they found that penalty by itself does nothing. You can't just tell a model, be faster. You have to give it the delta belief signal to teach it how to be faster.
Okay, this brings us to the results. The David versus Goliath part of the story.
Right, the fine-tuned model they call CIA, the Curious Information-Seeking Agent. They put their 1.7b version up against DeepSeek v3.2 on the test set.
Let's just frame that again. A 1.7 billion parameter model versus a 670 billion parameter monster.
Okay, so DeepSeek v3.2, its success rate was 14.35%.
That feels shockingly low for a state-of-the-art model.
It just proves that these huge generalist models really struggle with long-term focused reasoning. They just lose the plot.
Okay, so what did CIA 1.7b get?
24.8% success.
Wow. So the little model didn't just win, it won by over 10 percentage points.
It crushed it. And their slightly larger model, CIA 4B, got all the way up to 33.72%.
And how did this compare to a more standard RL baseline?
They ran it against STARPO, which is just standard trajectory level GRPO. CIA was way better. It's pretty conclusive proof that this dense turn level credit assignment is just a superior method for this kind of problem.
The paper has that really cool chart on belief dynamics.
Oh yeah, figure 5. It plots the model's belief in the correct answer over the course of the game. For the baselines, it's just a flat line. They're just guessing.
But for CIA?
For the CIA model, it looks like a staircase. Each question is a step up.
Step.
You can literally see it homing in on the answer, resolving its uncertainty with every single interaction.
Okay, but I know what the skeptics are thinking right now. Great, you just overfitted a small model to be really, really good at 20 questions. This is a one-trick pony. Did they test generalization?
They did. And this is where the paper, for me, goes from just interesting to potentially landmark. They tested it on 3 completely new tasks it had never seen before. First one, guess my city.
Similar concept, but the search space is totally different. Geography, not just words.
Right, and the strategy has to be different. The baseline models would just start guessing cities. Is it London? Is it Tokyo? Way too early. CIA, on the other hand, adopted a top-down search.
What do you mean?
It started asking about continents, then regions, then countries. It learned a hierarchical search algorithm.
So it learned the process of elimination, not just the content of the training game.
Exactly. The second test was murder mystery, a text game with 5 suspects, and you have to ask questions to figure out who did it.
So now you need logical deduction, not just filtering.
And the results here were honestly just a massive gap. The CIA-4B model solved the mystery within 8 turns nearly 98% of the time.
98%. And the baseline.
The standard supervised fine-tuned model was down around 30%.
That's not even close.
It shows it's really reasoning, systematically ruling out suspects. And then they did a practical one, customer service.
Trying to diagnose a user's problem.
Right. And the CIA model was able to dynamically adapt its questions to what the user said, homing in on the broken product feature. It beat the STARPO baseline by up to 15% on successful diagnoses.
But there was one chart in that generalization section that just completely blew my mind. The test time scaling.
Ah, yes. This might be the most important result in the whole paper. Remember, the model was only ever trained on games that are a maximum of 20 turns long.
It never saw anything longer.
But at test time, they just let it keep going for 50 turns. And normally, a model would just fall off a cliff once you go past its training horizon.
Right. Performance should crater.
But it didn't. The success rate kept going up. It didn't even plateau at 20. This means it didn't just memorize how to play a 20-turn game. It learned a truly general recursive strategy for reducing a hypothesis space.
It learned how to be curious, and it can just keep being curious.
It learned an implicit model of the world that lets it reason about its own ignorance no matter how long the interaction is.
I want to switch to the ablations for a second. For the people out there trying to replicate this. What were the dead ends? What didn't work?
A couple of important things. First, how you normalize the reward. They tried just using the raw values, and they tried TON squashing. Both failed. TON especially just removed too much of the signal.
Which is why the real U was the winner.
Right. But the most counterintuitive result was about KL divergence.
The KL penalty. That's standard practice in RLHF, right?
Yeah.
It keeps your tuned model from drifting too far from the original base model.
It's the safety rail, yeah. You use it to prevent the model from going completely off the rails and forgetting how to speak English. But here, it actually hurt performance. They got the best results when they removed it completely.
Why would that be?
Well, think about what the base model is. It's trained on the internet. It's trained to be a passive answerer of questions.
It's a prompt filler.
Exactly. To become a good information seeker, to become a detective, you fundamentally have to become different from that base distribution. Keeping it tethered to the base model was actively preventing it from learning the new agentic skill.
That's a huge takeaway for anyone building agents. The A-based model might actually be holding you back.
And the last point, like we said earlier, was that the efficiency penalty alone doesn't work. You can't just punish a model into being smart. You have to reward it for being smart.
So let's wrap this up. What's the big so what here?
I mean, on one level, we have a 1.7B parameter model that can run on consumer hardware but can out-reason a massive API call to a server farm. It's a huge step for making powerful reasoning more accessible.
Right.
But on a deeper level, this is a real shift in how we think about training. We're moving away from just imitation learning, just copying human text, and toward intrinsic reinforcement. The model is learning from its own internal process of resolving uncertainty.
It creates, as you said, interactively efficient agents. They don't just throw tokens at a problem. They perform surgical information extraction.
Which is what you need for any real-world application where you never have all the information up front.
The authors wrap up by saying this could be a path toward agents with implicit world models. And it makes me wonder if you can define curiosity as a reward for increasing the probability of your own correct beliefs. Are we seeing the first sort of primitive implementation of machine interest?
It's a fascinating thought. If an AI gets a reward for changing its own mind in the right direction, that starts to look a lot like genuine curiosity.
It walks like a detective, talks like a detective. Might just be Delta Belief RL. An incredible paper. That's all for this edition of AI Paper Podcast. We'll see you for the next one.